Greetings. The problem I want to solve for you today is a very classic problem where it is a choice. The problem gives you a choice whether to select a boundary around two or three even different systems, or just select boundaries individually around those systems and then see how you could combine them. The answer should be the same, but still boundaries around different systems would give us more details and more insight into the problem. So let's go straight to the problem. It's a problem that I once used for one of my midterm exams, and now I just write it, show it here. The problem tells us that there is a tank. This is tank A, and there is a cylinder next to it, and this is a cylinder, which let's call it B, and this is the cylinder. And the two are connected through a valve. Okay, so there's a tank, there's a cylinder, and the two are connected through a valve. Now we are given information about these two. The problem tells us that A has a volume VA equals 0.15 cubic meters, and it contains water as a saturated liquid, so X equals 0, and temperature T equals 220 degrees C, XATA, and these are all initial conditions. Initial. And then for cylinder B, initially the piston lies at the bottom. So VB would equal 0 initially. And then the valve opens. As the valve opens, water starts to flow from A to B. The weight of the B is such that it only starts moving after the pressure inside the B is 250 kilopascals. So PB equals 250 kilopascals. We could say that VB equals 0 till PB equals 250 kilopascals, and then the piston will start moving up. Now, the problem tells us that finally, now it's defining the final condition. Final condition, and it says the problem ends when P at A equals 300 kilopascals. So PA finally is 300 kilopascals. PB remains 250 kilopascals because the piston bears only a certain pressure, and if the pressure goes up, the piston goes up. And in fact, the piston weight and the pressure controls the pressure inside B. So that is fairly fixed. Okay, and then it says that there is heat transfer, and the heat transfer causes the temperature in both tanks to remain at 220. So at final condition, TA equals 220 degrees C, and T at B would equal 220 degrees C as well. Well, what the problem wants from us is to simplify the conservation equations. Just I would write it down here. The problem asks us to simplify the conservation equations. Then it asks us how much mass has left A. So 2, it says M2A minus M1A. Calculate M2A minus M1A. Calculate piston work, 3 piston work, or we could also calculate piston work because we know everything to calculate the piston work. In fact, this would count because there is no specific mass to state. Calculate heat transfer. 4, what is the heat transfer? And then draw a diagram. So 5, I will just write it here. 5, draw a diagram. In fact, you should draw the problem on a diagram. So these are the initial final conditions and what the problem has asked us. Now we shall move to follow just the very steps that I have always repeated that we should follow in solving every problem. Well, the next step is to decide on the control volume. And there are 4 different control volumes that we could select. We could select more, but the basic control volumes would be one would be A, and that control volume is, we call it A. The other one would be V, which is the valve, and the other one would be B. These are the 3 individual control volumes that we could select, or alternatively, we could select a different control volume, which is all the system all together. Sometimes selecting a general overall control volume gives us a fast answer. That's right. But and often when we select control volumes A and B individually, it gives us more insight into the problem and into what individual items do. Now, the next step is to, once we have the control volume, is to see if we could calculate or read the properties. But for the properties, well, it's very clear. We have TA and XA. So for A, For initial condition at A, we could know all the properties. For final condition, we have two properties, and we could read all properties. And for B, well, let's see what we can do for B. For B, it's not very clear at the moment here what we could have. For B, well, it's clear that to start with, there's nothing in B. So there's V is 0, M is 0, everything is 0. But for the final condition at B, we shall see what we have. So the initial condition at A, let's write it for A. And for A, what we have is T1. It is 220 degrees C plus 273.15. T1 equals 493.15 kelvins. X1 equals 0. P1, reading from, you could either use an application on your cell phone or read it from tables. You might read different values, slightly different values, if you use different books, since they enjoy different references, but still they will be very close. The one I read was P1 equals 2319.3 kilopascals, and therefore the pressure is very high. I mean, look, the pressure in A should go from 2319 to 300 kilopascals, and then the problem would stop. So this is why the pressure is so high, and then when the pressure gets to 250 kilopascals, then this piston will start to move. So we have these things, and then if we read other properties, the saturated liquid properties from any table, H1 would be 943.64 kilojoules. V1 is 0.00119 cubic meters per kilograms. This is kilojoules per kilograms, and U1 is 940.88 kilojoules per kilograms, and these are the values for initial condition at tank A. Now, the final condition in tank A is also known. So tank A, initial and final. At final condition, we know for tank A that P2 equals 300 kilopascals and T2 equals 220 degrees C. So we have both P2 and T2 with two independent conditions. We are in a good position to calculate everything from superheated steam. Why it is superheat? Well, at 220 degrees C, at 220 degrees C, the saturation pressure was 2319. And so if we are at 300 kilopascals, it is certain that it is superheat vapor. I shall shortly show it on the diagram and make it more clear. So H2 would be 2906.9 kilojoules per kilogram. V2 would be 0.749 cubic meters per kilogram, and U2 would be 2682.3 kilojoules per kilogram. So as far as tank A is concerned, all conditions, initial and final, are known, and all properties are clear. And let's see what happens for tank B. This is tank A, and let's see what happens to tank B. Initially, at least when it starts moving, before it starts moving, there's nothing happening. When it starts moving, V1 equals 0. This is initial condition. Once again, V1 equals 0, and that's all we know about the initial condition because there is nothing inside. But at final condition, we know that P2 equals 250 kilopascals and T2 equals 220 degrees centigrade. So we have two properties, two independent properties. We are in a good position to read the rest. And the rest would be H2 equals 2909.0 kilojoules per kilograms. V2 equals 0.9 cubic meters per kilograms, and U2 is 2683.8 kilojoules per kilogram. So we almost have all information regarding specific properties for cylinder at its final condition. I shall continue with the rest of this problem in part 2. Cheers.